All right, now that we've talked about acceleration or a change in speed, we can start to discuss Newton's second law. Okay? So Newton's second law is just the idea that the acceleration of an object by a force is inversely proportional to the mass of the object and directly proportional to the force. Okay, so what does this mean? It just means that if you have a heavy object, it's hard to move it, right? It's hard to speed it up, right? So the more mass something is, the harder it is to accelerate it, or the harder it is to speed it up or slow it down, right? But even if you have a heavy object, the more force you apply to that object, the more it will move. So that's all that's saying. So the formula for Newton's second law is that force is equal to the mass of an object multiplied by its acceleration, or multiplied by its change in speed. So the heavier an object is, or the more it's able to change a speed, or to accelerate an object, the more force it's applying. So generally speaking, if you have a piece of sand that's moving 50,000 miles per hour and slams into a spacecraft in outer space, so like a little tiny meteor, it would actually create a giant hole in that spacecraft. And that's because although its mass is low, it's a piece of sand, its speed changed from 50,000 miles per hour to 0 almost in a matter of almost no time at all. So that creates a lot of force. Just like how if there is a boulder slowly rolling down a hill, doesn't really matter how slow it is. If you're in its way, it's gonna crush you. And that's because the mass of the boulder is really high and it's not changing its speed very much. So if it's not changing its speed very much, you're going from standing still to crushed by a boulder really, really fast. And that's because its mass is super, super heavy and it's causing you to accelerate, okay? So that's the idea behind a force. Generally speaking, we deal with forces all the time. If some object comes in contact with another object, even if that object is air, it applies a force to it. Now remember, sometimes the force of friction or static friction can hold its own, right? So it's not going to necessarily move, but that force still exists because the objects are touching each other. We just don't necessarily see a change every time two objects come into contact with each other, but there's a change of their force. Okay, so Newton's second law, force equals mass times acceleration, okay? So if you have a mass of 50 kilograms and gravity is at a constant acceleration of 10 meters per second, how much force are you applying downward toward Earth? So let me just get this up and running real quick, get the workspace up. We'll open this up, nice. All right, so remember, force equals mass multiplied by acceleration. You'll also see it like this, F equals ma, okay? So force equals mass times acceleration. Nice, we've got an acceleration due to Earth's gravity. Remember, gravity is also an acceleration of 10 meters per second squared, so 10 meters per second squared. And our mass is going to be an object that has 50 kilograms of mass. So, what is going to be the force applied? 50 times 10 is 500 kilograms multiplied by mass multiplied by second squared. I'm sorry, by meters, not mass, sloppy, by meters. So kilograms multiplied by meters per second squared. Now, this is a lot to write here. So Isaac Newton was like, let's make this a little simpler. We'll call the unit of force newtons, all right? So Isaac Newton named this after himself. So the units are named after Isaac Newton, all right? So F equals ma, and remember that gravity is an acceleration, so weight is actually Newton's second law. So it's going to be a mass multiplied by the acceleration due to gravity. So that is a weight there, okay? I don't need that. All right. So Newton's second law. This is how we can separate Newton's second law from Newton's first law. So Newton's second law only takes place while two objects are interacting. So in this case, when a ball is kicked, if you measure the amount of time it takes for a ball to go from not moving to moving, it's really, really fast. But let's say an object is kicked and it goes from 0 meters per second to 20 meters per second. So a velocity of 0 meters per second to 20 meters per second. That ball, in the amount of time that it is kicked, reaches every speed between 0 and 20, and it will never skip any speed. So anytime an object speeds from 0 to 10 miles per hour, it reaches every speed between there. 1 mile per hour, 2 miles per hour, 3 miles per hour. It may happen really, really fast, but nothing can go from still to 5 miles per hour without hitting every speed between there. Okay, so Newton's second law is saying that if you kick a ball, it starts moving, right? So the force is being applied from the foot to the ball, and the moment that the ball breaks away from the foot, then we're dealing with just Newton's first law, because the ball is then moving at a constant speed in a constant direction, and that is Newton's first law. An object in motion remains in motion unless acted upon by an outside force. So until this ball reaches something else, another player, a goalpost, a goalie's hand, right? Or even if it's spinning and it's pressing on the air and the air is applying a force to it, then Newton's second law will start to kick in. But until then, it's only going to be Newton's first law, because that ball will continue moving in the same direction forever until something comes into contact with it. Okay, so a small force is going to be something that doesn't move something too much, and a large force is going to be something that moves something a lot. So in this case, the ball is hitting this guy's head and hitting this guy's head, and clearly he got hit a lot harder. Now, it could be due to the fact that this ball is moving faster, causing his head to move faster, right? Or it could just be the weight of the ball or the mass of the ball. A beach ball hitting into someone's head isn't going to do nearly as much damage as a bowling ball hitting into someone's head, right? Maybe if the beach ball was going 100 miles per hour and the bowling ball was going 1 mile per hour, maybe the beach ball would cause more damage. And that is only going to be due to force. Mass multiplied by acceleration, okay? So, again, how do we get the unit newtons? Newtons just comes from multiplying mass and acceleration, which gives us this crazy unit of kilograms multiplied by meters per second squared. So we just write N instead for a force, N, okay? All right. So that's the general idea behind this. We're not going to talk too much about this. All right, we're not going to talk too much about this because we need to start building some stuff. We're going to get into engineering. So I just wanted to give that little basic introduction to forces. The main ideas are that heavy objects are difficult to slow down and difficult to speed up. And something that changes its speed very quickly can cause a lot of damage, right? So just like how that sand example, a piece of sand flying through outer space at 50,000 miles per hour, hitting a spaceship going from 50,000 miles per hour to 0 really quick causes a tremendous amount of energy. Just like how a boulder, which has a lot of mass, slowly rolling down a hill, it can still crush people, and that's because it has a lot of mass. It doesn't need to change its speed much. It will crush, okay? Forces, mass and acceleration.